Let me begin. And to introduce myself, hey guys, my name is Max. I'm from Yandex Research and Higher School of Economics. These are a company and an institution in Russia. I'm going to present one of my works on volunteer computing in the context of deep learning. So basically, we've been doing some really interesting things about the connection between volunteer training and deep learning. Do you still see the screen or not?
No, the slides have closed. Here we go. Now they're back.
Yeah, let me just for 1 second. I'll just share the PDF to avoid any issues. Now, before we begin, I'd like to give all of you an example of what we currently achieved with all of our infrastructure and our algorithmic approaches. Here you can see the link. You can type it here or just send it in chat. Matt, if you could help me with that, I'd be very grateful. So it's just tinyurl.com collab v12. So what this link does basically is you can run and participate in a collaborative run of Albert training. Albert is a huge language model similar to BERT, and you can participate in that even from Colab. So basically, this is one of the demonstrations of our approach, and I'll give a bit more details at the end of my talk. So basically, what is the paper about? The one I'm going to discuss today. As some of you might know, the area of deep learning right now is facing some issues of scale. To put differently, we see a trend of training ever larger models on ever larger data sets, and this trend becomes more and more popular. You can see on the picture on the right that for the past 2 years or even 3 years, we see the parameter count going on an exponential scale, basically. And this trend does not see any immediate obstacles as of now. So it appears that we're going to see larger and larger models. And it was demonstrated that these larger models in context of language modeling, for example, have some interesting properties. For instance, some of you might be familiar with the OpenAI GPT-3 model, and it was shown that this model has zero-shot properties. Basically, you just give it any task, just say that you need to translate the text, for instance, and it translates the text. If you give some examples at the inference time, it can continue with what these examples are doing and basically generalize to many different tasks. So this area is this area has a very high potential. But what are the implications of this trend of scaling for any average researcher? Some models cost hundreds or thousands of dollars to train because of all the resource requirements. For instance, to train GPT-3, you might need tens of millions of dollars to afford or let alone rent a huge cluster. And it might be hard to train for an average researcher and to advance the entire field of deep learning, of natural language processing on the broader scale. Now, it might be possible for you, and there was a recent paper about pre-training a BERT-based model for hundreds of parameters. But if you decide to explode the parameter count to 100 billion parameters, it might be quite infeasible for you, even on an academic cluster. Now, what do we do with the situation? The inspiration for us came from the other sciences, basically. So all of us are currently the attendees of the BOINC workshop, so you might be familiar with the overall idea. The idea of volunteer computing, of collaborative computations has worked in other sciences. Why not use idle computing resources for deep learning as well? It turns out that there are some specific challenges in the context of volunteer computing, which are unique to deep learning. And they haven't been tackled in the in all of the previous distributed neural network training papers, basically. So here I listed three of them. The first of them is frequent node failures. For instance, some of participants might decide to leave the network at some point of the training, and you need to adapt to this paradigm and not lose any crucial parts of your network as the experiment runs. Another issue is communication over internet, because the connectivity speed here, as noted in one of the questions I heard, is magnitude slower than any HPC connectivity. So basically, you have to take this drastically slower speed into account for whatever experiments you're running. And the third issue is the issue of heterogeneous hardware, because all participants might have different GPUs, different connection speeds, so your network is significantly non-uniform in terms of connectivity and in terms of its composition. And as it turns out, all existing approaches for distributed deep learning, for instance, data parallel training, which is the most popular one, asynchronous training like Hogwild or other approaches. Model parallel training are not particularly suitable for this scenario because, for instance, some of them are not fault tolerant, which is crucial in our scenario. Some of them don't allow training huge models, and so we have this spectrum of issues. In our work, we try to restrict the possible range of architectures which we can train. But in exchange for that, we obtain higher scalability, and basically we satisfy all of the infrastructure requirements. Our approach is called learning at home, and for the outline you can see this picture. So basically, what do? We take this network of this huge neural network, which is composed of multiple layers. Each layer consists of several smaller parts. They are called experts. If some of you are familiar with the latest Google developments, you might know what I'm getting at. So we have these small experts, and these experts are located on many different computers. For any specific layer, you only need a small subset of experts to continue. You can distribute all these experts across the entire network. Basically, you can organize them in a decentralized manner via special data structures. And you can query this data structure to locate the required experts. I have a more detailed illustration. Let's just go quickly over that. So for any specific layer, we have a set of experts. These are like small subnetworks. For any given input, we only require a small portion of them. The decentralized mixture of experts differs from the regular mixture of experts in the sense that all of these experts are located in different computers on different peers of our network. And we locate these peers via something called a distributed hash table. This is a decentralized key value storage, basically, not to go into any details. And it might be familiar to those who have ever used any technologies like BitTorrent. So this is like the backbone of this technology as well. Once we locate these peers, we just send them the request for the input data for this layer. For instance, we aggregate their outputs and we average them according to the weights. That's it basically. And for training over the internet, we can trivially extend this paradigm to enable fault tolerance. Basically, you can see from this illustration that if some of the experts don't respond at either the forward pass or the backward pass, we can just discard the outputs and average whatever outputs that actually came to us. So basically, we are fault tolerant in the sense that if any expert fails to respond in a given time, this is not a problem for us. Also, we combine all of this with asynchronous training, so we query multiple experts in parallel and aggregate requests into batches on the server side. And that's why our approach is more suitable for volunteer computing than the methods I presented before. For the experiments in this paper, we have some prototype results which basically show that if we have large latency, which is quite realistic for the internet, this approach with aggregating the requests into batches and with the decentralized mixture of experts works quite well and outperforms trivial approaches. Also, we see that these asynchronous distributed mixture of experts updates don't harm training in any meaningful way. The entire architecture is scalable to more than 10,000 digit nodes, and the experiment which you are probably running right now utilizes maybe tens of them. It should be like 30. So for a conclusion, I'll just say that decentralized deep learning can be a viable alternative to training on expensive clusters. You can learn more at the link I've shown here. You can read the paper. It's accepted at NeurIPS 2020. Read the code. Everything is available, both the benchmarks and the overall code. And we also are actively developing the framework for decentralized training. You can access it. We have somewhat high code quality, and we're eager to respond to any of your requests if you are willing to try that. Also, I unfortunately won't have time for any detailed explanations, but recently we published a new approach, which is basically an alternative for data parallel training instead of model parallel, which I've shown previously. It's called Moshpit SGD, and it's also available on Archive and GitHub. Basically, it's a way to run all reduced algorithms, which are the core of all distributed training methods right now, in a decentralized fault-tolerant manner. It allows us to train models like Albert or ResNet, for instance, on tens of unreliable servers. For instance, some spot instances on cloud providers. And you can learn more via the link I've shown you on the first slide and participate if this experiment hasn't exploded already. Yeah, and on the right, you can see the plot. Basically, that's it. I'm ready to answer the questions if we have time, and you can see my contacts on this slide. I see that we have many questions.
Great. So many thanks. That was cool. If people would like to ask questions again, I'd ask to use the reactions button and the hand raise feature. In the meantime, I will actually ask you a question, which is if you could speak to the degree to which bandwidth in a volunteer computing context is limiting ability to scale, or how you're handling that?
Basically, the issue of bandwidth is quite important in the deep learning context because all of the distributed training requires quite a lot of data transfer. For instance, for the first paradigm, which I've shown here, you need to send the outputs of each layer, basically, right? And if your layer is quite huge, even if it takes quite a lot to compute, we can't just dismiss this issue. So how do we handle that? Basically, right now we have simple compression mechanisms, like convert all the data to FP16 precision, or we are currently running some experiments with even lower floating point precision, but this is ongoing work. And basically, well, I hope I answered your question. So the issue of bandwidth is quite important to us, and we are actively trying to resolve it with some methods like compression, for instance, and other techniques.
Okay, great. One other question or that I have just as curiosity is to take actually relevant to this slide, which you have up here, is your mixture of experts slide. And the concept of mixture of experts reminds me of a Marvin Minsky book from some time ago about AI called Society of Minds. And I wonder if you're familiar with that. As his concept is that human cognition actually is basically a hierarchy of distributed experts in the brain.
Thank you for bringing up this book. I'd be happy if you could send it to me, like the name, because
Okay.
the idea really seems similar to what we're doing, and like this entire approach is currently gaining some popularity in the deep learning field. So yeah, there could be some similarities, but unfortunately, right now I'm not qualified to answer that question.
Okay. Well,
I have to dive into this book.
I'll send it to you, but the one feature of that is potentially quite interesting is that in his concept, the mixture, the experts, expertise is a hierarchical concept. So an expert would be comprised of sort of lower scale experts.
Of lower level experts.
Yeah, and so you create skills by wiring together existing experts in different ways.
Yeah. So basically, you're suggesting that we could have lower level experts at some point, and then we can have the combinations of those experts, which can learn even higher level of functions. Yeah,
That's right.
I'll send you the archive link in a moment. Both of them, actually.
Okay.
I saw the question.
Yeah. Meanwhile, there's a question from Mohanty, but Mohanty, I'm going to say, don't ask your question right now because you're going to be on the panel, and the whole point of the panel is for you to ask each other questions. So if you don't take it wrong, Mohanty, I'm going to lower your hand. Do we have any other questions, or should we move on to the panel? So I think the panel. So Max, if you could suspend your screen share.
Yeah.